So welcome to my session, Forensic Container Checkpointing and Analysis. My name is Adrian Reber. I work at Red Hat since 2015. I'm involved in process migration, which is the basis for container checkpointing for at least 13 years now, I think. The tool we are using today in the demo especially will be CRIU, and it's all about CRIU. CRIU, I'm involved since 2012. This is the low-level tool which does the checkpointing of processes and of the containers. And I'm focusing on container migration since around, I don't know, maybe last 8 years. I will give a bit background about checkpoint restore and CRIU and where and how it's used, then some use cases for container migration, then the demo and how to do the forensic container analysis, and then some future. Especially this is in the context of Kubernetes, because I have moved the ability to checkpoint and restore containers from the lowest level up to the highest level, and at this point I'm at the container orchestration level. Checkpoint restore in user space, CRIU is the tool we're using. The reason for the name is in user space is because checkpoint restore is a technology which exists for many years, also in Linux, over 20-25 years at this point, I guess. And it was mainly coming from high performance computing initially, and there were different approaches. There was an external kernel module helping with it. Then there was a lot of system call interception with LD preload. So this was all. The problem with those approaches was basically, if you talk in the scope of checkpoint restore, it was not completely transparent, because at the time you started your process, you needed to prepare the process to be checkpointable and restorable later. So the goal was to come up with a completely transparent checkpoint restore implementation, and I think around 2005, 2008, there was an in-kernel approach. It was really a big patch set, around 100 patches, and it was not merged in the end because it was touching every subsystem, and the community was not really happy with that approach at that time. Looking back today, maybe it would have been easier than what we do today with CRIU. But anyway, so that approach in the kernel was the checkpoint restore in kernel space, and the next approach was CRIU, checkpoint restore in user space, and that's why we have the name today out of the history, and also because how it works without any real kernel support. So there's no specific support in the kernel to support checkpoint restore in user space CRIU. There are a couple of changes CRIU introduced into the kernel, which CRIU needed to get information easier out of the kernel, but all those added interfaces are not 100% checkpoint restore specific, so there are other users of those new interfaces. There are multiple integrations of CRIU now for many years in different container runtimes, container engines, container orchestration, and the first one to mention, which I personally never used myself, is OpenVZ. They were building system containers long before the name container even existed, maybe, for that type of thing. And they were looking for a way to migrate their system containers from one host to another host for fault tolerance or for load distribution and things like this. So they invented CRIU for their container engine. The good thing about CRIU is that CRIU, in contrast to all other approaches before, was developed with containers in mind. So the goal was to migrate containers, and not like with the approaches before to support high-performance computing for fault tolerance, or for the same reasons, basically. Another big user, which I also have never seen myself, is Google's container engine Borg. So they integrate checkpoint restore into their container engine. The only thing I know about is from conferences where Google talked with us upstream CRIU about what they do internally. So from what they told us, they used to have they have a lot of containers running there internally, and before CRIU they just when resources were getting low, there was some high priority tasks, maybe something interactive running on one node, and there was a low priority task, then they just killed the low priority container, and they had to restart the work on another node. And with the introduction of CRIU, what they do now is they just migrate the low priority task to another machine, and so the high priority task can continue to work without with getting all the resources it needs. The example they've listed was, one of the examples was YouTube re-encoding, which they do in the background, and so if they migrate it, then they don't have to restart the whole encoding process. So that's one thing where it's used. Then there's LXC integration for CRIU for many years. This was also one of the first container engines, container runtimes supporting CRIU, checkpoint restore. As far as I know, they don't use it so much actively, and this is mainly because system containers are more complicated than application containers like the OCI containers, and so there's more resources CRIU has to manage, and so the chance that it fails is higher in LXC than in simpler application-based containers. Then there's a Docker integration for many years of CRIU. Podman has support for it. That's what I've been working on the last couple of years. And the reason to get it into Podman was because there's also CRIU, the Kubernetes runtime. And first I got it into Podman. That was easier because there's no dependency on Kubernetes. So, and the code between Podman and CRIU is not the same, but it's similar. So I was able to also implement it in CRIU. And then the last step was to get it into Kubernetes. I was not aware how complicated the Kubernetes development process is. So what I did, I wrote code, I submitted a pull request, and nothing happened. And then I was told, you have to write a Kubernetes enhancement proposal. So it's a long text document where you clearly describe what you want to do, and you have to socialize it. And so I tried to do that, and I wrote the proposal. So the first two links are the proposal. And the idea was, because checkpoint restore container migration is something which is, if you're looking from a container perspective, or especially from an application container perspective at it, it's not something you maybe think you would need, because containers are supposed to be stateless, and if it's stateless, then you don't have to migrate it. So there's a lot of maybe philosophical different viewpoints if this is actually needed. So we had to come up with a story how to integrate container checkpoint restore migration, hopefully at some point, into Kubernetes, and the story was forensic container checkpointing. The nice thing about forensic container checkpointing is that it's also useful for stateless containers. The idea behind forensic container checkpointing is you have a container running on your system, and at this point it's independent if it's Kubernetes or Podman or Docker or whatever container engine you have which creates your checkpoint, because all the things I do later in my demo you can basically do with any container or even just a process. But the idea is your container, your process is doing something which it should not do, at least you believe it should not do, but you don't want to look too closely to it. Maybe there's some attacker will remove the code if he sees that it's been analyzed. So forensic container checkpointing gives you the chance to take a checkpoint without a container, the process knowing that it's checkpointed. You can write it to disk, you can analyze it in a sandbox environment, you can start it in a sandbox environment, and the original container will just keep on running, and it will never know that a copy of it's being analyzed somewhere else. The third link is the actual pull request for Kubernetes. The fifth and fourth are just documentation how to use it in Kubernetes, and the last one is how to use it in OpenShift. Was just released, I think, 2 days ago, this article. So let's talk about a couple of use cases why checkpoint restore or container migration might be useful for your container setup. The simplest one I came up with is basically reboot and save state. The last article here, the the use cases for container checkpoint restore, container migration were actually proposed by ChatGPT, and ChatGPT came up with 8 reasons why you need container checkpoint restore. Anyway, so the reboot and save state is something, so you have your system that is running a kernel, you need to update your kernel for some reason, but you also have a container running on it. The container takes some time to start, and you really, I don't want to reboot it, it takes forever to boot up. So what you can do is you can update your system, then you can take a checkpoint of the container, you write it to disk, then you can reboot the system is gone, and then it comes back with a new kernel, green kernel, everything is fixed, and the container can be started really fast. I can talk a bit about saved startup times in my next example. It's a bit the same, like it's quick startup. So you have a container, maybe you have a application as a service or something like this. And you want your customers to use your containers, and they should not wait too long. So there's actually a couple of companies using CRIU to exactly do this. They have some software which takes like 10 minutes to initialize in the container, Java and databases and all the things like that. And what they do is they basically take a copy of the initialized container, write it to disk, and once someone requests the service, they can quickly create a copy of the container, and the time saving is from 10 minutes original initialization down to 15 seconds or something like this, because it's basically we're just reading all the memory pages back into memory without any logic around it. And in the end, the startup time only depends on the size of the memory page. So if you have a lot of memory, then it will take longer. If you have just a small container, it will be faster. Container live migration is kind of the combination of those two use cases, maybe. So you have a source system and a destination system. You have a container on your source system, and you want to move it to the destination system. It's a stateful container. You don't want to lose the state. Maybe you have hardware problem on one system and you want to move away your containers, or whatever. So you can take a copy of the container, transfer it to the another system, and then start one or multiple copies of the container. Another interesting thing which I never was aware about for what checkpoint restore might be useful, and people are actually using it, are spot instances. So you have spot instances from Google or AWS, and they are supposedly really cheap, but they can go away in like 2 minutes or even shorter time. So you can use CRIU checkpointing to checkpoint your container regularly, every 50 minutes, every hour, or you can just checkpoint a container when there's a signal coming from the infrastructure that your VM is going down, and in that moment you can move or save the data to some external storage and then continue using exactly that state on some other spot instances without losing your work because the spot instance is going away. Another interesting thing I just recently saw when there was a video from Microsoft about ChatGPT, how they train their models, and they actually, it was interesting to see that they actually mentioned CRIU for their training models. The interesting thing is that the training is using, most of the time is using GPUs, and using GPUs with CRIU in combination is not working most of the time. Because CRIU can get all the information from the CPU, we can get all the register, all the states out of the kernel of the operating system, but there's usually no standardized way how you can get this information out of the GPU. So 2 or 3 years ago, AMD came along, and they provided a plugin for AMD GPUs to support checkpoint restore. But in the ChatGPT video, Microsoft spoke about AMD GPUs and NVIDIA. So it sounds like they are using CRIU in combination with NVIDIA GPUs, but we upstream CRIU have never heard about anyone working with CRIU on NVIDIA GPUs. So I don't know. Maybe it will come at some point, but from my point of view, it's not. At this point, it's impossible to checkpoint a restore process. If it's using the GPU directly, the NVIDIA GPU with AMD, it might work. So let's go to forensic container analysis and the demo. So what I will do now in the demo is I will start a container. I will use the container a bit. It's a stateful container, so that it would make sense even if I want to migrate it. And then I will checkpoint the container out of the pod. So it will be running in a Kubernetes environment. I will checkpoint the container, and then we will we'll look at the details, what you can find out about your running container. So it's a stateful container. There's a question?
Yeah.
Sure.
May I ask already?
I have no problem with it.
What's the downtime when migrating a container?
So many years ago, I measured exactly this, and the downtime is basically the time you require to move your data over your network. I was using InfiniBand 32 gigabit network at the time, and writing the data to disk on the destination system and restoring the container is so much faster than the data transfer time. So it's, I think even today probably you will be limited by the time you need to move the process or the image of the process from one host to another host. And the image size is dependent mainly on the how many memory pages the application uses. And if you're doing it in the container use case, then there's the combination. What we also collect in our checkpoint also here is all the files that have changed in contrast to the original container image. So if you have a lot of file changes in your container, then the checkpoint image will be really big. But the memory pages over the network is the thing. Yeah, and I'm using OpenHPC. That's an OpenHPC container. That's a project I'm also involved in, and so I'm using this to calculate pi in my container so that I have something stateful there. So let's go to my demo screen. It's not here. Oh, there it is. So I said I'm using Kubernetes here, kubectl, describe. So there's nothing running. I have a really simple setup here. It's no. It's like this. Good. So it's basically a pod with two containers in there. Both are stateful. The first one is a Wildfly. It's a Java-based application. I'm also doing including this here, and the second one is the Pi application I'm checkpointing now. So let's start this container, this pod. So it has started, and now I can talk to it using curl. So I'm just getting the IP address, and then I'm talking to it, and then basically I'm getting the current value of pi. It's calculating in the distance to the real value it should be. So it's definitely stateful, and whenever I start it, it will start from the beginning. It has a few additional interfaces. I can write a secret, some random data, some data to the memory of my container. So this is my something like a password maybe, which is in memory, which I want to later find in my checkpoint analysis. And then I have another interface which can create files in the container, so just that we later see that there have been files created. Just calling it test file and test file 2. So now I can create a checkpoint with the Kubernetes thing is still a bit complicated because the problem with the checkpoint is now you have all of a sudden all memory pages on disk, and everyone can now potentially read your private keys, your random numbers, whatever. So it's everything now on disk. We create the checkpoint archive only readable as root. So the situation doesn't really change because as root you can access the memory anyway, and the file is also accessible only by root. But the big difference is now you can take the file and move it to some place else, and then maybe somebody else can access it. So at this point, checkpointing is only available as a kubelet API and not as if you're using Kubernetes as from kubectl. So let's create a checkpoint. The checkpoint has been written. So let's do It's basically just a tar file. It's a tar file. We will unpack it now and have a look at it. But first, my slides say checkpoint control. So checkpoint control is a tool we wrote to analyze checkpoints, to make the analysis a bit easier so that you don't have to look into all the details yourself. And the nice thing is checkpoint control started as something I wrote 2 years ago, and we were lucky to have 2 great Google Summer of Code students this year, and they really enhanced it. Now it's a really useful tool at this point, so this is really something great out of the Google Summer of Code mentoring project there. But so checkpoint control, show $. I'm just making this a bit smaller so that we can see the table. I will change the font back. So it's even still too small, I don't know. So basically what we see is we see the container name. I don't see it myself.
One question. Checkpointing it will automatically stop the...
No, the container keeps on running.
It keeps on running?
Yeah.
Okay.
So this is different. If you're using... So if you're using, I know for Podman, if we say Podman checkpoint or container, then the container will stop, but you have a flag, an optional flag, which tells it keep running. So you can create a checkpoint on Podman and Docker, and it will keep running, or you can stop it. For the Kubernetes use case, we went, it's always running because the story around this is the forensic container checkpointing. So it's not about migrating containers, it's just about taking a checkpoint. We can still, with the checkpoint, migrate a container to some other host, but we have to stop it manually on this host. There's another question, yes?
You said it continues running. Is there any interruption or interference visible for the latencies?
Probably yes. I wanted to show this later, but let's show it now. So checkpoint control, because this is whatever. Let's show it now. So no. So CRIU collects information about the time the process was not running. So this is the extended version of checkpoint control, and I have to pipe it through less. So what you can see here is it says CRIU dump statistics, and you see the time, the complete time the process was frozen, the time CRIU took to stop the process. So freezing time is the time required to stop the process, it's short, but the complete frozen time for this process was 119 milliseconds. You see how much time we required to write the pages to disk, and how many pages we scanned, how many pages were written to disk. And this is the time required on a VM running on my home system for 18 megabytes of memory. So there will be a downtime because the process is stopped during the time when we write the memory pages out. So
the downtime is proportional to the memory size?
Yes, this is the main thing CRIU has to do. It has to scan all memory pages, decide this is a memory page which has been changed, I will write this to disk. This is a memory page which hasn't changed, I will not write it to disk. Okay. But yeah, so the table we have seen before gives you the information about the container name, the container image it's based on, the container runtime, the container engine, the IP address, and the size. We also see the size here. You see the checkpoint size is 18 megabytes. It's the size of the CRIU image. Then we also have the root FS diff size here, somewhere here. Here it is. This is the size of the file system changes, because I only changed 3 files. This is really small. But yeah, now I'm confused. Anyway, so this was checkpoint control. But what we also can do is we can unpack the checkpoint manually. And then we can look at the image files that CRIU created using CRIT. CRIT is a CRIU image tool. It can show you all the information CRIU collected during checkpointing of a process. So let's just unpack it, and then we see. And then we see what files are in the tar archive. So bind mounts is basically just a description which bind mounts are mounted into the container, which we have to restore later. We need to track those for restoring because if a bind mount is a file, then we have to create a destination upon restore as a file. And if the bind mount was a directory, we have to create it as a directory. Because the container runtimes, they basically just create directory for everything you want to bind mount into the container. So, and the kernel doesn't like bind mounting a file on a directory. So this is just some additional information we track there. Then the file config dump is basically what Checkpoint Control was printing out in the table. It's just some high-level information about the container checkpoint. Then there's the dump.log file, which is the file CRIU creates when doing the checkpoint of all processes. So basically, this is something you need if the checkpointing fails for some reason. Then spec-dump is the file of the specification of the container. If you ever used runc, there's config.json. This is basically config.json with some additional information to later recreate the container as it was during checkpointing. And statsdump is the file which we just saw with the timing of the checkpointing and the memory pages written. And let's have a look at the root fsdiff tar. This is the file which contains all changed files in contrast to the original image. And we see it's just a log file and 2 test files. And if I look at one of the test files, it just contains the thing I wrote to it in my test container. It just says test file. So it's just an example how you will see all changed files in your container checkpoint once you want to analyze it. And the main thing here is the checkpoint directory. This is the thing CRIU creates. CRIU uses mainly protobuf to store all the data about the processes which were in the container. There are a couple of other things here, like if we look at, now we can do it like this. There are these tempfs images here, and if we unpack it, we see basically this is the content of tempfs files. So if you have a container, if you have a tempfs file inside of your container, then CRIU will collect all the information, put it into a tar file, and it will be part of the checkpoint. This is now /dev probably from the content. If you have a bind mount of a tempfs which is outside of the container, then we will not collect the tempfs outside of the container. We will just remember that we have a bind mount to some location on the outside of the container, and it's basically your task, if you want to restore the container, to recreate the content on the outside of the container as it was before. But let's have a look at those protobuf files. The one easiest thing is maybe, or simplest thing is, if we look at the information about the UTS namespace. This is basically just the host name of the container, and we see its counters is the name of the pod I selected here. But we can also look at the PS tree. PS tree contains all the process IDs in the container, and it contains the PID, the parent PID, GIDs, and all the things like this. And we can have an easier look at it if we do something like so. I don't see it here. Nobody sees it. Oh, okay. Let's try to, okay, now we can see it. So those are the PIDs of the processes running in the container. The interesting thing here is CRIU always collects the PID information from within the PID namespace and not from the outside of the host. If we now look here at what's running on my system, we can see I have the last 3 processes are the processes of my container. And if you look at the PIDs here, you see it's some much higher number, because that's the view from outside of the PID namespace, but CRIU always remembers the PIDs within the PID namespace. So if we restore the container later somewhere, the containers within the PID namespace will be the same. The containers outside will just be something random we get assigned. So we know our PIDs now, and And now we can look at details of the processes we checkpointed. So for example, let's look at so we have core files which contain the core information about the processes we checkpointed. And let's have a look at those. No. And we see all the register states of the process at the time we checkpointed it, and floating point, and now it seems my SSH session is hanging, and then we see SE Linux labels, restartable sequences, capabilities, all the things collected here. The interesting one interesting thing might be have a look at what processes were actually running in the container. So we can loop over our images, and now we see we had one process called bash login wrapper, one bash, one py, and one t. Those are the 4 processes we had. So now we have the name to the PIDs we found in the image. This is the short value, which is collected from proc-pit. The longer version, which you see also in the PS output, will be seen later because you need copy that information from some memory pages, actually. So then another tool we're using to analyze our container is grep. I wrote some information to the memory pages. Now I can just use grep to find this information. So this is my private secret data I've written to the pages, and the pages are basically a raw dump of all the memory pages, which you can look in a hex editor. And if you know what you're looking for, then you can use grep. If not, then you just probably have to go through the whole thing and maybe find the information you're looking for. But the important thing is you have access to all memory pages of the process. Another thing you can do, there's a script in the CRIU repository. It's not distributed in any packages, RPMs, or Debian packages at this point, because it was never used. So it was written a couple of years ago. It converts the checkpoint images into core dumps. And basically what I can do now is use GDB to have a look at the information here. Now I also see the complete command line here of my process, just as it was during checkpointing. And I can use GDB to look something like, I don't know, the registers. And again, it's the same information we were getting from the images before, but you can do all the GDB things you do in GDB now with this core file to have a closer look at it. And with this, I'm also at the end of my demo. So let's talk a bit about what's next. What's next is basically, at this point, is mostly in the context of Kubernetes, because this is now the highest level I have reached after many years working on it. kubectl checkpoint I talked about before. It's only exposed as a kubelet API because there's still some uncertainty if having all the memory pages on disk is such a good idea. So I have something prepared locally. I have to open a pull request and see how the community reacts to another pull request from me. Then another step would be Kubernetes uses pods where multiple containers are running. Pod checkpoint restore would be a nice thing. Then I've done this a couple of years ago as a proof of concept for kubectl drain. So this is basically just a loop over all containers in a pod, and then some metadata for the pod. So this is not a technical challenge. Most things at this point don't feel like a technical challenge anymore. It's just convincing somebody to review the code and finding the right way which doesn't break everything or is even future-proof, things like this.
Have you implemented it in Podman?
I started at some point, but I don't know if I finished it. So I did something for pod. I don't remember it. Yeah. Then maybe if we can checkpoint restore containers natively in Kubernetes, then we can do kubectl migrate. Maybe there's a scheduler integration at some point, so it will do things like the Borg container engine if resources are getting low priority containers are moved somewhere else. Then I started some time ago an effort to get the checkpoint image standardized. So I didn't mention this, so I always talked only about forensic container checkpointing. But we found a way to trick Kubernetes into actually do container migration. So we, out of the tarball I have here to do the analysis, I'm able to create an OCI image, and this OCI image is defined by what I thought was right. And that's why we wanted to have this as a standard defined, and we tried to talk with the image spec project, but there's not much going on there for a long time now. So the thing is, what we do is we just put the tar file, some additional metadata into the OCI image, and then we can later restore it. And for Kubernetes, it basically looks like we're pointing Kubernetes to an OCI image in some registry. Then Kubernetes tells the engine, CRIU in our case, to start a container. CRIU will detect, okay, this is a checkpoint, I have to do something else. It will do a restore of the container. Kubernetes will think it's a new container, but it actually is a restore of the container. But in this, we're trying to standardize it because Containerd, they also have their own image format, which we couldn't use because it uses internal structures of Containerd, which we didn't want to have in CRIU. So the hope is to get something where we have the checkpoint information from CRIU and maybe some JSON files to describe it and not in protobuf encoded here. So the summary of my session today is basically CRIU can checkpoint and restore containers. It's integrated in different container engines for many years now. It's used in production more than you probably expect at this point. Use cases I talked about is reboot into new kernel without losing container state. We can start multiple copies of one container quickly if we have a long time to initialize. We can migrate running container. We can use it for spot instances to hopefully save some money. And in Kubernetes, it's available under the label forensic container checkpointing. And this is the number of the Kubernetes enhancement proposal. And with this, I'm at the end. Thank you for your time and happy to answer any questions or more questions.
Have you experimented with essentially using this as a core dump handle? So we could have mutual independent HTTP, and I'm wondering whether we can just checkpoint and crash and not have the entire container to debug.
Oh, that's funny, yes. So instead of creating a core dump, creating a checkpoint, something like this, yeah. No, we never even thought about it. Good idea.
So we talked about use cases that you have found for migrating container workloads and everything. Do you also have maybe some use cases already for the forensic part in Kubernetes implementation?
Some use cases?
No, so like some examples of where it's actually used.
No. This is so the forensic use case is something actually I think Red Hat customers have asked for. There are I think there was a bank and some national security thing in Switzerland which are interested in having this to analyze the container without stopping it to see if some attack is going on. So there is interest for this there. That's why we came up with the story. So because I was always focusing only on the checkpoint restore migration thing, and this forensic container checkpointing came from outside to me.
Maybe to add to his question, I've encountered in the CTF a challenge where you're given a checkpoint, the exact tar you've created, and inside this tar file you could do, or going around because I wasn't aware of the structure that you've explained, but going around you'd find like some traces that leads back to a C2 server, and then you had to do some port knocking in order to try and get back to the C2 server, but I couldn't get like much further, and I just didn't get anywhere at the CTF. But it was an interesting challenge, and I believe that, I guess, as you said, more companies are going to get interested in having this.
Yeah, I think analyzing the raw memory pages is definitely a challenge. You need to know what you're looking for. So I think this is really hard. But at this point, it gives you an easy way to get the raw data to start the analysis at least. Yeah.
Okay, thanks.
There's one more question behind you.
When it comes to scaled deployments or stateful sets, like with multiple pods, how does CRIU scale? Like I can imagine a pod consisting of multiple containers. Each container would have the same priority, which in return would mean that if my CRIU operator, I guess, for some reason finds out that that the pod should be moved, will all the containers be moved or only a few, or how does it work?
So this is in completely unimplemented territory we're talking about, but a container wouldn't be moved as a pod needs to be moved as one complete thing. I don't think you can split a pod between hosts because they share namespaces and other resources. So yeah, the thing would be we would need to move the complete pod.
Could it be possible to build a tool that works like volatility or not?
Oh, so I heard these questions before. So this is some forensic analysis tools. So there was a question a couple of months ago, I think, that if the memory dump has the same format as the tool you mentioned, right?
Yes.
Yeah. I've never heard of the tool, so I don't know. So what we do is a raw dump of the memory pages. We have another file where we say which address of the memory page dump has to be mapped back to which address in the memory when we restore the process. So I don't know what the tool uses, how it works, no idea.
Okay, so it depends, I guess,
Yeah.
on the dump methodology. Okay, I'll try to have a look. Thanks.
Sure. Okay, thank you. Oh, no, another question here. Perfect.
Yes, with the migration between, yes. Maybe can you just hear me like this? I'll speak in the microphone.
For the
mic for the stream.
For the
right.
recorded
Okay.
stream.
Are you migrating live TCP connections?
So yes, CRIU can do this. The thing is the IP address has to stay the same because if the IP address changes, then you cannot migrate a connection because the connection is bound to the IP address.
I did 10 years ago. I used CRIU. I was wondering this thing exactly, and I'll talk to you about this offline.
Sure.
But you can do it.
You can do it, but the thing is, I think I don't know much about Kubernetes in the end and how you deploy it, and it always feels like it's really complicated with many layers in between. And so I don't see much value to have a TCP connection from the outside into the container if we migrate it. So if we have a connection between containers in a pod, this makes sense to keep that alive because it's probably using localhost or something like this. This is easy. But from the outside, it's technically it's possible, but I think the complexity of Kubernetes is just so high that I don't know if
they'll never accept it.
Yeah. No, I think I don't know if you can even track it. What is the IP address inside, and if you move it to another host. So, I don't know. Yeah, I think we have to go.